Hello, welcome back to this series on discrete calculus. This is video number 4. Looks like there's going to be 5 total. One more after this one. In this video, we look at writing polynomials in terms of falling powers and why we care. How we're going to use the fundamental theorem of calculus to work to find the sum of a bunch of polynomial terms by replacing them with falling powered terms. I'm going to show you 2 ways to do this problem. First up, we're going to write this cubic polynomial in terms of falling powers by substituting. We're going to be able to pick an n equals 1, and then 2, and then 3, and then figure out what a, b, and c are. Okay, and we'll find a different way to do it on the next slide. And you just figure out which way you like best. All right, great. So here we go with plugging in the n values, like n equals 1, for instance. Left-hand side, it'll be just 4 plus 3 plus 5. Right-hand side, anytime you see 1 falling in anything that's bigger than 1, it's going to be 0. So a times 1 falling 3, that's a times 0. B times 1 falling 2, that's b times 0. C times 1 falling 1, anything falling 1 is just the number itself. And so that means that 12 is equal to c. Great. We got to pick a different value. So we'll pick n equals 2. All right. Well, numbers get a little large on the left-hand side. On the right-hand side, though, 2 falling 3, 2 falling 2, 2 falling 1. We know what c is. We can go ahead and plug that in now. Anytime you get 2 falling 3 or anything falling something that's higher, 0. Anything falling itself is going to be that factorial. And anything falling 1 is just that number. So on the left-hand side, we got our 32 and our 12 and our 10. We'll put that all together on the left-hand side. On the right-hand side, 2 falling 3 is 0. 2 falling 2 is 2, factorial, which is 2. And 2 falling 1 is also 2. Okay, so we get our 24, 2b on the right-hand side, and then we end up with 54 on the left-hand side. Subtract the 24 over, you get your 30. Divide by the 2. You got it. B is 15. All right, worst case scenario, we're going to plug a 3 in. We're going to find out we don't really need to do this, but let's do it anyway. So we have 3 cubed and 3 squared and 3 on the left-hand side times 4, 3, and 5. 3 falling 3, that's 3 factorial, 6. 3 falling 2 happens to also be 6. And 3 falling 1 is just 3. So we got a bunch of numbers here. We got a 90. We had 36 on the right-hand side. We can put those together as 126, subtracted away from the 150 that's on the left-hand side. And it ends up with 24, divide by the 6. Yes, a is 4, but we should have known that already. The only time you're going to get a cubic is from the 4 n cubed. Therefore, the coefficient in front of the n falling 3 should also be 4. So when it comes to the last falling power, or the highest falling power, just match the coefficient on the highest power in the polynomial. Okay, matching. Okay. All right, great. So if you see 4n cubed plus 3n squared plus 5n, you're going to replace it with 4n falling 3, 15 falling 2, and 12 falling 1. We're going to see it used in a second. This is approach number 1. If you like it, you go with it. Approach number 2 requires you to have the formulas in hand to what n falling 1 is, n falling, what n is in terms of the falling powers, n squared in terms of the falling powers, n cubed in terms of the falling powers. So you have to have that handy, and then you just plug them in and just distribute and collect the like terms. 4n falling 3, but then 12n falling 2, and then 3n falling 2, so 15n falling 2. Okay, get the same result as last time, and less sweat. Okay, but it requires you to memorize or have on your note sheet these beginning powers and their representation in terms of falling powers. Now, let's take it one step further. Let's throw this inside of a summation, use the fundamental theorem of discrete calculus, and be able to find this sum. Our sum is 4n cubed and 3n squared plus 5n, our same polynomial. We're going to add that up as n goes from 1 to 8. It's manageable by hand, but no, you're not going to do it by hand. we want to do it using our formulas. Okay. All right, great. We found how to write this particular polynomial in terms of falling powers. We did it 2 different ways. Okay, so 4, 15, and 12, A, B, and C. We have these falling powers. I wrote them in color-coded here because we're going to end up using the fundamental theorem of discrete calculus on each of the terms. Okay. We know how to do the antiderivative or the anti-forward difference of a falling power. It's like the power rule in reverse. N falling 3 is the forward difference on N falling 4 over 4. N falling 2 is the forward difference on N falling 3 over 3. And N falling 1 is just the forward difference on N falling 2 over 2. Okay. Pull out these constants, the 1/4 and the 1/3 and the 1/2. Make them interact with the coefficients, the multipliers A, B, and C. And we got a nice formula here then, which says that, it's just the sum of these falling powers. Forward difference falling powers, though. We're ready. Fundamental theorem of calculus on the next slide. We're going to break it into 3 different sums. We don't have to do that, but it works out nice. And so we'll do the FTDC on each of these. We'll have 8 falling 4 minus, 9 falling 4, right? Plus 1, don't forget the plus 1. 9 falling 4 minus 1 falling 4. Then 5 times 9 falling 3 minus 1 falling 3. 6 times 9 falling 2 minus 1 falling 2. But we know those ones falling whatever that's higher than 1, we know those guys are just zeros. Okay. Leaving us with 9 falling 4, 5 times 9 falling 3, 6 times 9 falling 2, which is a good answer. Okay. But if you want to get it down to the actual number, we need to go a little further. What is 9 falling 4? 9876. So the falling power tells you how many you have. The number tells you what you start with, and you just keep taking away 1. So 9 falling 4, 9876. 9 falling 3, 987. 9 falling 2, 98. Still looks a mess. Still don't want to go to a calculator yet. We can factor out, though. Everybody has a 9 and an 8. Leaving us with the 7, 6, that's 42. The 7, 5, that's 35. And the 6. Those add up. End up as 83, 72, and 83. Okay, maybe now I'll go to a calculator. Or just write it out long ways. There's something that, we used to ask on a quiz. It's reasonable. Okay. The sum, n equals 1 to 8 of 4n cubed plus 3n squared plus 5n is 5,976. A computer can do it for you using Excel or whatever. But no, you could do it with your brain and using falling powers and the fundamental theorem of discrete calculus. In the next video, we want to work integration by parts into this. The digital version of integration by parts called summation by parts. Let's go ahead and end this video now. Thank you for watching. My name is Nakia Rimmer. A bunch of students that aren't even my students asked me to make this set of videos, and they're modeled after Dr. Grice videos, and I'm happy to do this for you, and I hope you like it. Please like and subscribe and comment down below, share, and I'll see you in the next video. Take care. Bye-bye.